This is a video for MEI Core Pure Mathematics, Vectors 5, Further Lines and Planes, 5.6, the perpendicular distance between two parallel lines. If we want to find the shortest distance between two parallel lines in 3 dimensions, the technique we use is to find a point on one of the lines and then use techniques that we've seen before to find the perpendicular distance between that point and the line in 3 dimensions. The two techniques we've seen before use either the scalar product or the vector product. And it doesn't matter which of these two techniques we use, but for this video we're going to use the vector product technique. For these two lines to be parallel, then either the direction vectors are the same, or one direction vector is a scalar multiple of the other. Okay, here's my example. I've got two lines. This is L1 and this is L2, and this one is in IJK form and this one is in Cartesian form. So let's just unpick those a little bit. I'm going to convert L1 into column vectors. So the line L1 is R is equal to 1, 4, minus 1 plus lambda lots of 2, 2, 4. And for L2, well, to unpick Cartesian form and put it back into vector form, each of those parts is equal to some parameter for the equation, which I'm going to call mu because I've used lambda in the first one. So x minus 2x mu, y minus 4 equals mu, and z over 2 equals mu. Rearranging these, I can get x, y, and z in terms of mu. So I'm going to get r, general vector x, y, z, is equal to mu plus 2, mu plus 4, and 2 mu. And now I can put that into a vector form like L1. So r is equal to, the known point in here is the constant bits, 2, 4, 0, plus mu times 1, 1, 2. And now if I look at the directions, well, the direction of the first line is 2, 2, 4, and the direction of the second line is 1, 1, 2. And I hope you can see that D1 is just twice D2. And so, therefore, we know they're parallel. Okay, so now I want to choose a point on the first line, so that's L1, and the point I'm going to choose has got position vector. I'm going to use its known point, 1, 4, minus 1. And for the second line, L2, I'm going to use its known point, which is 2, 4, 0. And for the direction vector for the second line, I know that D2 is equal to 1, 1, 2. And so we can now take each of these bits. This is the point, this is the line. We want the perpendicular distance from this point to this line using this technique that we've seen before in a previous video. Okay, so there's the summary of that. So 2, 2, 4, this has been written up in IJKs, 1, 1, 2, they're scalar multiples. In fact, the first one is twice the second, so we know they are parallel. And then we're choosing points for the first line, that's the 1, 4, minus 1 point, 2, 4, 0 for the second line, and the direction vector 1, 1, 2. So moving on to see how that works out. This first bit here is p minus a, so that's going to be 1, 4, minus 1, minus 2, 4, 0. That gives me minus 1, 0, minus 1, so that's that one there. And this is the direction vector. That's this bit over here. And that's all just been plugged into this formula. Work through the cross product. We get this. That's root 3 over root 6, which is just 1 over root 2. And rationalizing the denominator, multiply top and bottom by root 2, we end up with a distance of root 2 over 2. So this technique is really just a special version of from a point to a line. Pick a point on the first line and find the perpendicular distance to the second line. The next and final video in this sequence is 5.7, the perpendicular distance between skew lines.